welcome to your lecture. So this is your first lecture in class on Unit 0. You guys have already covered, well, I guess you did watch a short lecture on experimentation if you needed that. You at home watched a lecture on unit conversion, SI units and prefixes, and tying into that scientific notation. I expect you to be quite familiar with all this. Just a big idea. Scientific notation, we always keep the value. We're just changing the representation of the number, okay? So you're not actually changing the value at all. You're just changing how it looks. It's kind of like text language. Instead of saying love, L-O-V-E, you say L-U-V, okay? So maybe that's old school. Maybe I'm aging myself. That was what I wrote in junior high. When, you know, you text your girlfriends, you're like, I love you. And then, we talked about unit conversions. Big idea, old units must cancel. This will become incredibly important when we hit up unit 4, stoichiometry, okay? Actually, we might have stoich. Yep, stoich is in unit 4. So this will become very, very, very important for you to understand is how to track your units and set up your stoichiometric dimensional analysis unit conversions. I'm going down the line of how it builds, okay? And measuring temperature, we mainly work in Kelvin and degrees Celsius, but Kelvin is the true unit for measuring temperature because temperature, as most of you know from physics, is a measure of kinetic energy. What if there's truly no kinetic energy? Only Kelvin accounts for that. 0 Kelvin is truly no energy. So you need to memorize the conversion factor. 273.15 plus degrees Celsius is how you go from degrees Celsius to Kelvin. Notice, do not put a degree symbol with Kelvin. All right, so now let's talk about, okay, could you staple and give it to Jose? Did you get 2 copies? Because I asked for.
No, I didn't pay attention past like.
Could you please? There were 2 copies.
Oh.
Well, I found one in my backpack.
Okay, perfect. So then go ahead and give it to Mitchell. Okay, so now we're going to talk about how else do we represent numbers, particularly precision in numbers, all right? So the big idea here is, let me move my food, my chow mein.
I really need to stay.
Okay, that's good. Is we have to recognize that there's a ton of errors, right? As you guys know from your first lab, Bunsen burner lab, there's a lot of errors that we saw. Intensity of flame. No one actually, like, you all had different levels of flame. You also singed my speakers quite well. So my lab period 4 TA had a fun time cleaning that one. And there's just also a lot of mistakes that can happen. Human error. Your naked eye is very unreliable. Fun fact, your eyes never stop moving. So if you try to stare at one thing, you'll notice it starts shaking because your eyes are evolutionarily trained to always look for motion that could attack you. But we call, we label, I guess, error as either systematic or random. And sorry, the spacing is awkward. But the idea here is that systematic is consistent. Okay, and this affects more accuracy. This is more of an accuracy effect because what happens is all of your numbers are off. You're quite precise usually because you're consistent, but all your numbers are shifted up or down or whatever. Okay, and then there's random error, right? Like your lab partner, like drops the sample in one of the trials. That's a random error. Okay, it's a temporary. I think I misspelled temporary, but that's okay. Temp or error? Temporary or temporary?
I think if we know what the word is.
Temporary. Okay. And this is usually the result of outlier data, right? This is where you get your outliers, and this is more of an attack on precision. When you're looking at error in the lab, some of the biggest common types of error that I've already mentioned is human error. Okay, forgetting to calibrate, calibration error. Or your calculation errors, right? That's a pretty systematic one. What if you memorize the conversion between Kelvin and Celsius is 283, not 273? You're gonna have a systematic error in your reported values, right? Interesting, interesting. I almost thought it was me, but I think it was Kyle. So, yep. All right, so, you've probably heard of this old school is that we tend to say when measuring, when looking at your measured values, okay, the last digit in a measured value is the uncertain digit. which makes sense, by the way, because it's the one that's always between the lines. You're like, is that a 2.34 or a 2.32? You got the 2.3 part. You just didn't have great confidence in the last one. That's usually the naked eye kind of helping you. Instruments are just the same. It's where we get the plus minus error margin in a lot of research papers and stuff. So we actually calculate, I'm sure you guys are familiar with this, percent error. So here's the equation, percent error equals your experimental minus your actual all over your actual. And by actual, I mean what should have theoretically been gotten. So for a lot of your experiments, you guys, there is a right answer. And your goal is to try to get to the right answer and have your experiment confirm that that is truly the right answer. It has actually already been confirmed for you by 100,000 scientists. But what you'll often notice is that you might be asked to calculate percent error and be like, how off are you? And if it is like more than like 5%, you need to talk. You need to talk about that. Okay. So go ahead and just do this problem for a second and then we'll just compare answers. So hopefully that was nice and simple. Good. Liam, shout out your answer. What'd you get for the percentage?
9.6%.
9.6%. Can I ask why you stopped at 0.6? Why the first digit place after the decimal?
Because we only had one digit in our starting answer. Oh, we actually had two, but it's a percent, so I didn't want to give.
Okay.
Yeah.
So you got 9.6%. What would it have been if you went to the second digit?
9.62. Actually 9.63.
Okay. Percent error. That's 10%. Imagine if you got 10% bonuses. That's a pretty significant thing. Okay. I wish I got a 10% bonus. So here's what we're going to talk about now is sig figs. Why did I ask? Why do we care about where we stop in our numbers? How many of you guys are familiar with sig figs? One, because you studied from honors a little bit. This is going to be the bane of your existence because it's just tedious. And what? The AP exam report asks you to report all answers in sig figs. So, sig figs are, dun, da, da, da. It is a method of, I'm just saying number, numerical representation. Okay. That communicates precision in your or of your measured / calculated values. So, general rules, and you must memorize them. One, all non-zeros are significant. We call any non-zero digit a significant one. Zeros before a non-zero are not significant, aka we call them leading zeros. It's kind of like when someone leads you on, okay, non-significant. So 0.00063, okay, all of these would be considered leading zeros, non-significant, but we do not get rid of the number. Like they're placeholders for the fact of keeping your value the same, but we wouldn't consider them significant. They're just getting you to the right value, but they don't actually hold that much meaning for you, right? So next one, zeros between non-zero numbers are significant. We call those sandwich zeros. It's kind of like when you meet people and they're like, right, Netflix movie, high school drama. There's always that one friend in the popular group that you're like, how are you popular? It's just the effect of being sandwiched by popular people, according to Netflix high school dramas, which are very inaccurate. Okay. And for an example, if this was a number that I gave you, 7.006, all right, your sandwich zeros right there would be considered significant. Zeros following a decimal only after a non-zero digit are also significant. So again, here, when you look at this, those zeros, if there was not a 6 after it and there was not a decimal before it and there was not a 7 before it, would be considered insignificant. But because it came after a non-zero plus a decimal, it is significant. Okay, last rule, zeros following a non-zero with no decimal are not significant. We call those trailing zeros, like you're trailing behind, right? What is that called? The caboose of the train? Oh, when you go on hikes, I'll be the caboose. Trailing zero. So for example, the number 6, 0, 0, 0, 0. These are all trailing zeros. We would consider them insignificant. But that all changes. That all changes when you add a decimal. Now everything's significant. So this is why it's very important to look at the end of your number, because we would now consider these significant. Just simply because of that decimal at the end. Okay, so let's look at a couple more examples. I want you to do these on your own. I want you to determine the number of sig figs. For our first, number 2, I had said the leading zeros. That would be a 2 sig fig one. For the 7.006, that would be a 4 sig fig one, according to our rules. For number 5, that would be a 1 sig fig number. But if we add the decimal at the end, that is now a 5 sig fig number. So let me give you some problems. I want you to identify the sig figs that go for these numbers. Okay, just take about a second or 2. Let me do the testing of my name skills. If I look at you and I say your name correctly, give me a thumbs up. So, stop it, Julian. Ethan, first one, how many sig figs and what rules did you use?
I took 5 because of rule 4, zeros following decimal after a non-zero.
Excellent. 5 sig figs, SF. This is not San Francisco, folks. SF, because of rule number 4. Okay.
Do we have to know the numbers associated with it?
No, I'm just trying to help you see that in the example. Okay, next person, Quinn. How about the next one? What'd you get?
I said 4.
Because which rule number? Because of rule number 3. Excellent. This is an awkward pause. Don't worry, future classes. I'll figure it out. I feel bad. Hold on, I feel bad. Rainier. Okay, Rainier. What is the next one?
1 sig.
Fig. 1 sig fig? Why? What's the rule?
Rule number 5.
Rule number 5. And last but not least, Nathan.
I put 4.
Okay. Rule. Rule number 4. Thank you, Hayden and Nathan, for teaming up on that one. So when you're multiplying or dividing, how do you report numbers? Because most of the time you're not going to get one number and be like, I'm done, right? Raw data versus calculated data. Okay. Oftentimes, whatever you collect in lab is just to get the information necessary to plug it into an equation that actually gives you an answer with a meaningful value. And that means that you're going to be multiplying, dividing, squaring, all that good stuff. So how do you report a final answer to the correct sig figs? And here are a couple of rules. When multiplying or dividing, we say that you report your answer, ANS is my shorthand for answer, to same sig figs as least sig fig number. So it's kind of like saying on a team, right? You're only as good as your weakest teammate, which is a little rough, okay? Because there's some gaps in there. But For example, if you're doing 6.4 times 2, your final answer would not be, oh no, math, 12.8. But instead, it would be 10.
What?
Yep. Yep. Because there's only a 1 sig fig variable in your calculation, so you'd have to report your final answer into a 1 sig fig answer. So you couldn't even put the dot at the end, 10 point. No, 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 that's a 2 sig fig number. So now you're down to a 10. That's right, folks. That's right. Basically, what we're saying is you better get your precision together or else you're going to get some scary numbers like this. Okay, now for some of you, that's encouraging because what if I've had some people argue via sig figs their score and I was like, sorry, that doesn't apply to your grade. But how about when adding or subtracting? It's a little bit actually different. So for your answer,
Why can't rules just be the same?
I didn't make these rules, trust
No,
me.
it's the math rules.
Report your answer to the least precise when adding or subtracting, which often, by the way, is usually your lowest sig fig. It often aligns. So for example, okay, 6.4 plus 3.12 equals 9.52. I could actually only report this to 9.5. And it also technically already aligns with my lowest sig fig in general. But you'll see instances where it doesn't match perfectly with low sig fig. For example, I can't think of one right now because you put me on the spot. So thank you. I saw it in a couple workbook problems and I don't know where. You'll find out. So
What is the difference between least precise and lowest sig fig?
there's always a couple examples that I saw a while ago, but I cannot pull them out of my hand because now you're making me nervous asking me on the spot. Yes.
Precision would be like
Like decimal
multiple-
points.
I mean, if you could have like a really, really, really big number that's like 0.1 and then like, you know, okay, I get it. I get you.
You feel me? You picking up what I'm putting
I
down?
am picking up what you are putting down.
That's right, folks. That's right. Okay, and then finally, conversion factors. We love conversion factors. Pretty much any derived unit. Do you know what a derived unit is? Any derived unit value? No? No? A derived unit.
Isn't that like
2 units combined.
like 2 units, like miles per hour?
Yeah, miles per hour. Any unit that is really made of multiple units, but acts as one unit is a derived unit. So whenever you see a derived unit, sometimes I get nervous and you'll see a shaky handwriting. I'm really not that shaky. It's the pen, but I do think it's a little bit of me. So derived units, I started going shaky on you. Is any time that you see like 2 units in 1, so grams per milliliter. That is always, by the way, a potential conversion factor. Any derived unit value is always a potential conversion factor. And by the way, we treat conversion factors usually that have already been established, okay, as not impacting your sig fig count. So for example, right, 2.54 centimeters is 1 inch. We would not actually consider it all the sig figs of this. It is only based on your measured, calculated, or given values because usually in a problem, your given values are considered assumed to be measured or calculated. Okay, so be careful not to account for your sig figs. If you have an answer that's measured at 4 sig figs and you use a conversion factor that's 3 sig figs, forget the conversion factor sig figs, go with the 4 sig fig. Okay, so that's all I have for you. Psycharoonies, there's one last thing. Did you all carefully acknowledge in my pre-lecture when you're preparing for your sig fig unit conversion and scientific notation quiz, the idea of if you have a squared or cubed unit that you have to also square or cube the conversion factor? Lord bless. Okay, now we really are done. Good job, guys. This is for future classes too.